name is Joan, and I'm here today with my fellow teachers, Mayunga and Joseph, as we take you through a topic which is fundamental not only in mathematics but also in modern life, and that is orthogonality of inner product space and Schwaz inequality and its properties. So, as we introduced the area, we are going to look on the orthogonality of inner product space and the Schwaz inequality and its properties. In each task, we are going to see the application in real life, the mathematical technique, and how it works. By starting with the orthogonality of the inner product, the definition and concept is that the linear algebra and vector spaces, two vectors are orthogonal if the inner product is 0. Mathematically is the inner product of vector A, B equal to 0. Then the vector A and B are orthogonal. That is to say, they form a right angle like in a 90-degree triangle. For example, in a 2-dimension in Euclidean space, let A equal to 1, 0 and B equal to 0, 1. Then the dot product is 1.0 plus 0.1, which equal to 0. Since the dot product is 0, vector A and B are orthogonal. That is to say, perpendicular to each other. Now, we are going to see the application in real life, which is noise cancellation in audio technology. Imagine you are using noise cancelling headphones. This device detects the unwanted external sound wave, which is noise, and it generates a sound wave that is orthogonal to it. When you combine, they cancel each other out effectively. The mathematical technique in this part, let any vector any be the noise wave vector, vector s be the sine vector, which is music. For perfect cancellation, the inner product of vector n, which is noise wave, and the vector s, which is sine wave, equals to 0. This means that artificial noise sine created is orthogonal to the actual sound, ensuring there is no interference with your music. Now take a look in this diagram. We can see there is a vector u, which is 3, 1, and the vector v, which is -1, 3. When you take their inner product equals to 0, that means there is no noise. The noise is cancelled. So that's how the inner product of the orthogonality of inner product is used in noise cancellation.
Yes, let's now shift to another part, which is Schwaz inequality or couch Schwaz inequality. So couch Schwaz inequality states that for any two vectors A and B, that is the magnitude of inner product of vector A, B is less than or equal to norm vector A dot norm of vector B. Equality hold only if the vector are linearly dependent, such that one is a scalar multiple of the other. Real life application is that here hiring process and candidate matching. Imagine a company trying to match a job candidate skills vector A with a job requirement vector B. The more close aligned this vector are, the more suitable the candidate. Take an example from the diagram, which is hiring process. When we take about the magnitude of vector A and vector B is less than or equal to the norm of A dot norm of B. Its application is that candidate profile and job requirement description are often converted into future vectors. For example, skills, experience, and education. The cosine similarity between these vectors is calculated using the inner product. Cosine similarity is derived from the Schwaz inequality. That is, cosine of an angle is equal to the inner product of A, B over norm of A dot norm of B, bounded by the inequality, which is magnitude of inner product of A, B is less than or equal to norm of A dot norm of B. A higher cosine similarity means the candidate closely match the job. In summary, Schwaz inequality underpins the math behind matching a logarithm and the bias detection tool used in modern hearing system. Thank you. This is an end of our presentation.